Start recording. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday we covered how to use the hardware renderer to actually render all the sprites that we were rendering in software before. And now what I would like to do is I would like to go ahead and finish the implementation of that, because we did a bunch of it actually, because there really wasn't that much to do. I'd like to go ahead and finish today at least the part that doesn't involve texturing, because the texturing, like I said yesterday, is really going to be the only part that's complicated. And when I say complicated, I'm not talking about the drawing. Drawing with textures is, as you saw, extremely easy. Really, I'm just talking about getting the textures down to the card in a streaming fashion. That is really the problem that we will face. So yeah, that's excuse me. That's where I'd like to be at the end of today. So I'd like to jump into it right away and sort of get to the point where we're only worrying about the textures, so that we can talk about that tomorrow. So day 239 is today. If you want to unpack day 238 source code, that is what we'll be working with today. Here we go. So here's Handmade code, handmade.cpp. Go ahead and build. And if you remember, we created an OpenGL file. In the OpenGL file, we just sort of started laying out what we would need to do in order to make things render through OpenGL. And as I think everyone hopefully agreed, it's a really basic set of things. Like what you're looking at here is the entire thing that we need for a hardware renderer for Handmade Hero. Very, very little code at the moment. And that might grow a little bit over time, but on the whole, 2D games don't usually have to do too much work to make a hardware renderer. I mean, let's be honest, it wasn't that much work to make a software renderer for a 2D game. 3D games tend to be a lot more intensive because there's a lot more bookkeeping that goes on and a lot more sort of fuss involved in the 3D. So although pretty much all the principles are the same, there's just enough more in 3 dimensions to fuss with that it can be a little annoying. But for our case, we don't have to worry about those because we are in 2D at the moment, or at least 2.5D at the moment. And so all of our problems come typically further up the pipeline, where we have to think about how we want to deal with 2D, and not so much at the rendering stage where everything does bake down into a sprite that we put on the screen. So here's the rendering code that we wrote. And if you remember correctly, we had to do some stuff to make sure we would be able to work in screen space in our concept of screen space. We did that yesterday by setting the projection matrix up in this way that we did here, right? We tested it and then used it here. So really, all I really need to do at this point, if I want to make sure that I can render in hardware like this, is I just need to do something, right, to connect the pieces of code that are currently not connected, right? Essentially, I've got some code that I would like to run in OpenGL, right? And architecturally, I know that if I was just to use this to render to the screen, it would work, right? But what I don't have is a good bridge from the place where render group to output is actually called, which is here. Actually, there's a couple of different places it's called, right? There's one here, and there's another one for when we do ground chunks and stuff. But that's, what's going on at the moment, right? So the question is, how do I bridge these things? How do I bring these things together in a way that allows me to have the renderer be something that works through OpenGL as well as through software? And there's a couple different ways that we could do this. I think at first, what I might suggest is I'm going to kind of do it in the way that people often would do it first. And then I'm going to maybe discuss a little bit with you why I don't think it's a very good idea that we do that, and how we might improve it. Just because sometimes on Handmade Hero, I feel like if I go right for the solution that I feel is the most effective, if it happens to be something where I'm fairly confident, that solution is right, sometimes it takes away the benefit of you seeing the not very good version, which makes it hard to appreciate why the other version is better, right? So if it's something that I haven't really done much before and you get to see me work through it, that's very valuable because then you can see how I get to a reasonable solution. But if it's something that I kind of know how I think it should be done, you don't get to see that. So I think what I might do is sort of avoid the correct solution first and sort of show what most people probably would do in this circumstance. And then we'll sort of try to move to something that's better. All right, so here is our situation. When we render to the thing, we call this tiled render group to output. Now that's the only place that tiled render group to output is called other than in the debug system, right? So if you take a look here, you can kind of see what the situation is, right? There's tiled render group to output. So I'm going to go ahead and just take a look at that and see if we can just literally port it directly, okay? So when we call tiled render group to output, instead of calling tiled render group to output, what I'm going to do is insert essentially a mitigation call, a call that sort of hops in between those two, that will either go to OpenGL or to our software render depending on the circumstance. And so what I can do is I can insert in here, right, inside our Handmade render group, what I can do in here is I can insert a call that will, in fact, I can even do one better than this if I want to. I can actually even make a plat version, but I guess we'll do that in a second. So what I'm going to do in here is I'm just going to, inside render group, I'm just going to make a thing here that basically mimics this function. So the tiled render group function, tiled render group to output, this guy. What I'm going to do is I'm going to make a copy of this that's basically a sort of a shim that can switch either way. So instead of calling tiled render group to output, I'm going to call something which is just called like render to output or something like this, right? And then inside here, what I'm going to do is I'm going to switch to see which one of these two renderers I would like to use, right? So I'm going to look at the render group and I'm going to see, for example, which is hardware or something. And if it's hardware, then I'm going to do an OpenGL render group to output. And that's going to take all this stuff. And if not, then I'm going to do the old tiled call. Now, I feel like I probably, I could be wrong, but I feel like I probably actually want to make this one step more removed in a way. And the reason for that is no matter which one of these you're calling, we would want to call our sort function. And if you remember, the sort entries call actually happens in these two areas here, right? Tiled group to output and render group to output. That's where those get called. And so really what we want to do is this is what we would like to be calling. We'd like to be calling that regardless, right? So we kind of want that to happen no matter what it was we were doing, and then we would do these. Render group to output is the non-tiled version, and that one at the moment, we don't really even know if we're going to keep that one around. It depends on whether we leave the ground chunk system in place or whether we kind of get rid of it. We don't really necessarily know how we're going to do it one way or the other. But and so in this particular circumstance here where we have OpenGL render group to output, again, I'm just going to sort of pass it through. Okay, so in this case, we know what all of these things should be, right? We've got render queue, render queue, our render group, we've got our draw buffer, and we've got our temp arena. And then for OpenGL, we have no real need for the render queue at the moment because there's no multi-threading that's going to happen there. So we really just have the render group, and then we have the temp arena, which it might need. Honestly, it probably doesn't even need that, so at the moment we could probably just leave it with that, if that makes sense. And so at some point we need to call into that, that function. Now again, we probably don't want to start polluting the sort of all of the rest of our code with includes for OpenGL and stuff like that. So what I'd like to do is just do a slight sort of, wall that off just in a slight tiny little way. And say that inside Handmade platform now, we can do something where we, inside all of our platform callbacks through here, we will have one more. I guess, so we don't have too many. We're pretty, this is a pretty reasonably small number. Like I said, I'd like to keep this pretty small. But there would be one more that we would add here, and it's not too bad necessarily. So I'm going to add one more here, and I'm going to do a to-do Casey temporary, right? Because we're going to talk about this in a little bit. So I'm going to have a thing here called platform OpenGL render to OpenGL. And I'm going to go ahead and make a typedef for that. And we're not even going to make a macro for it, because this is going to be, like I said, something I want to discuss. And I don't necessarily want to expand on it immediately. So we're going to leave it a little bit as a little bit of a zygote for the moment. Okay, so we have our struct render group, and here's that render group. And now we've got our platform OpenGL render that we can call, right? So that in our OpenGL code here, that's going to be this. We don't need the output target or the clip direct. Obviously, those aren't even used. And so this already fulfills exactly this signature. So in theory, all we would have to do to make that actually work is actually register the isHardware part and then go from there, right? So let's go ahead and take a look at render group. I'm sorry, at OpenGL render group to output. Let's change that to be our platform code. I don't remember exactly how we define that stuff from working, but we're just going to call this render to OpenGL. I don't know if we call it platform API or what it was. I guess it was platform, yeah. So we're going to call that off the platform. And now we just need some way of doing isHardware. So for right now, I'll just lock it to calling isHardware, but we'll take a look at that in a second. All right. So now if I went ahead and ran the game, obviously we should just crash at that call immediately because it's a 0, right? It should just jump to 0 and die. Okay. Does someone want to tell me how that just happened? What just happened? How did that not crash? Set a breakpoint. Set a breakpoint, people. WinMain. Where is that actual code? Where is the code? Where? I ask you. So here's load game code. Here's process begin messages. Am I wrong? Should that not have just jumped straight into nonsense land? I feel like it should have. Record input, game update. That's what we actually want right there. So inside game update, in theory now, right, we're... Well, yeah. As you might have expected, if you never actually change the call site, you don't actually call the new function. I know that's pretty shocking. All right. Let's try that again. Okay, that's what we actually wanted because we haven't set this yet, right? So now what we should be able to do is we should be able to come in here in our Win32 Handmade. We should be able to include our Handmade, this file right here, handmade OpenGL.cpp, to put this code into our game. And we're going to have to go fix all the compilers there. But once that happens, then we will have like our, all of our thing where we fill out all of our platform pointers, this right here, can go ahead and fill out that platform pointer as well, right? Render to OpenGL. Oops. And that's going to be, well, I guess it's just OpenGL. Let's call this OpenGL render group to output. Here we go. Okay. So all we need to do now is actually make this stuff compile properly. Obviously, this timed function bit should go away for now. We need to include Handmade render group here because otherwise we're not going to have any of those specifications. The output targets, I guess that's true. We don't know what the width and height actually is if we don't have the output target. So maybe we actually do need the faux output target there anyway. But that's kind of something that, again, I guess we'll sort of see why that's something that we probably want to address, again, with some of the changes that I said I wanted to make. But OK, if we pass the loaded bitmap output target to this guy anyway, like so, then that would take care of that temporarily anyway. But we need to add that to the stuff that gets passed here. OK. So yeah, getting closer. Our output target should just have, I believe, just a regular width and a height, probably, I'm guessing. Yep, and it does. Let's go ahead and fix that here as well. And then our OpenGL rectangle call, everything needs to be v2s, but of course they're not. So we should be able to take care of that pretty directly, like so, by just picking out the 2D portion of things that aren't 2D, if that's actually what it's complaining about. What is it complaining about? XY is not a member of v2. It's not? Really? What did I do wrong? Oops, that's no good. So those guys are in Handmade platform, right? In here somewhere. Oh, okay. So I never did the XY versions. So no, they're there. So is that not a number of v2? So which one of these guys is a v2 that actually shouldn't have been? What was the complaint? What are we complaining about? Oh. Well, all right. I just misread the error. Those guys are v4s. Why are they v4s? That doesn't make any sense. That's just a complete nonsense thing that we typed up there. All right. So now we have an OpenGL render group to output version that we can call, which in theory means we should possibly be able to run now, also hopefully without crashing. But we don't actually have any textures enabled. So the only thing that will actually work is solid rectangles, right? That's the only thing we would ever actually see on the screen in theory. Because, you know, let me see if I can actually... Two things about that. That is true, but we actually have to call it. We actually have to display the OpenGL. If I remember correctly, we never actually switched back to this path, yeah? Yeah. So this is all still running at the moment, right? Which is not what we want. If this will clear, this was the thing that was drawing our buffer, which we're no longer updating. So we need to get rid of all of that so that now we should be able to see a bunch of solid nonsense on the screen, if that makes sense. Yeah. So that's exactly what we should see for now. Again, because almost everything on the screen is something that we don't actually have the ability to draw since we don't have any of our texture stuff working. But at least we should, in theory, be going through that path now. Like I said, at least in theory. So let's do a very simple way of just sort of getting the textures working, just so we can take a look at what that might entail, so that we can make some educated decisions. Like I said, I want to kind of talk about how we do the integration here. But until we actually get it working a little more solidly, that's not going to be very useful, right? So we have our clear, that's probably correct. We have our rectangle, that should be, I believe, also working correctly. Although I don't actually know. We would have to test it, certainly. So the main problem we have is just this part right here where we're trying to draw an actual bitmap. And remember, we actually do know exactly how to draw the bitmap, right? We have it here. So what we could do if we wanted to be extremely slow is we could actually just bind a texture and submit the texture every frame, right? Incredibly slow, incredibly bad idea because we don't want to be sending the texture down every time. But we actually could totally do that, right? And so the way that we would do that is, again, right before we call our rectangle call, we would do something like this, where we're literally just going to do exactly what we did before. We can bind a texture, as we found out, which I didn't realize. You don't actually need to allocate these. So we can just pick an arbitrary texture handle to bind. We can submit whatever the image texture is that we want, right? So the entry bitmap, we can literally just send it down right now and say, hey, send it over the bus every single frame, like so. Set it up, turn on texturing, and render. Okay. And again, absolutely awful idea, but in terms of actually getting something on the screen, in theory, it should actually work. And as you can sort of see, it almost does. There's a reason why it doesn't quite, but as you can see, very, very slow. It probably wouldn't be quite so slow if I switched to the game, because then the textures are smaller. Although, for some reason, I don't see anything when I switch to the game. Although I do see things when I switch to the cutscene. I don't know if you can see it, but you can actually see that the cutscene graphics start to come in here. Incredibly slowly, right? I mean, you can see just how slowly that is doing its thing there, right? Really, really bad. But it's working, right? So, I guess another thing that we should mention, you can kind of see what's happening with the screen here. If you notice, we're not getting any of that transparency. We're not getting any alpha blending at all, right? So that's something that we have not discussed how to do in OpenGL, but it's something that we're going to have to turn on, right, if we want that to happen. So I would first go ahead and explain, let me first go ahead and explain how that works, because it's actually quite simple, and then we'll turn it on. But again, like I said, it's not just me saying that this is a really bad idea. You could see just how incredibly slow that was. The reason it's so slow is every single one of those plates of the cutscene had to get transferred over the bus every single frame, which is just way too expensive for this card to handle. All right. And to be clear, it's not just the transferring over the bus, it's also the remapping of it into the format that the card wants and all sorts of stuff like that. All right. So let's go ahead and cover blending here. So as you saw, right, incredibly slow, but it was working, not doing any alpha blending, and obviously we need alpha blending for our game. So what do we do about that? Well, the problem with alpha blending is as follows. We have, like I was saying before when I sort of drew out the GPU diagram of how everything works, we have a couple programmable pieces, right? There's sort of like a geometry portion. If you kind of looked at the stack of like stuff comes in and stuff comes out of the GPU, right? This is the GPU. We have a geometry portion, right? And this is a bunch of shader code. This is shader here. And when I say the geometry portion, I don't mean geometry shader. I mean everything involved in geometry, like tessellation shaders, all those sorts of things that we haven't covered and maybe will never cover on Handmade Hero because they're not potentially all that relevant to us. But maybe, you know, you never know. We then have code that operates on vertices in here, right? We then have code that operates on pixels. Okay, and that forms the full programmable stack of a GPU pipeline, right? Something comes in here, it gets munged into a bigger something here, it gets transformed in some way here, turned into two pixels, like where the coverage is, and each pixel has whatever happens here executed, which then produces color values, and something happens to the color values. All right, very, very broad overview. We talked about this a little bit. We'll talk about it again. But point being, that's sort of the very, the sausage pipeline, if you will, of a modern GPU looks a lot like this. And what happens is, in the way that we're doing things now, like I said, this is the programmable version. We are using the fixed function version, which basically has preloaded, you could think of it as preloaded programs for everything in here, right? So we don't have access, we can't write any of these shaders or anything, because OpenGL, with the version we're using even, doesn't have support for any of that, right? Later we will load in a higher up version of OpenGL, and we'll put some shaders in there. So later we will be using this, but right now we're not, okay? But, so this is basically like OpenGL's code is doing all of that portion, and OpenGL's code is doing all of this portion as well. Okay. The reason I bothered to draw this out is because of this part right here, which actually, even on today's hardware, is often very, very similar to what it was in the fixed function days. Meaning, all of this stuff became programmable. The part right here still remains very non-programmable on a lot of GPUs. Some GPUs it's more programmable. But on a lot of GPUs, this part, not programmable. What that means is that after the pixel colors are determined, what happens to them as compared to what's underneath them, right? So remember how we do our drawing. There's like, here's our frame buffer. And this is just like when we wrote it. Here's our frame buffer. Here's our sprite that we're trying to render on there. There's stuff underneath here already, right? The degree to which the stuff that is underneath can be fed into the shader is actually extremely, well, I even shouldn't say limited. It doesn't, basically. It's a fixed thing that happens in here, for the most part. You just simply don't actually get to use it in an arbitrary way. That's just the way these work. So what ends up happening, typically, is if you want to do arbitrary operations on things that are in the frame buffer, it doesn't work this way. What actually happens is the frame buffer is actually another thing that you're writing to, and it actually has nothing in it, and you pull from a texture that is the existing stuff in the frame buffer and whatever you're doing, and you like pull from two textures and combine the two textures arbitrarily and then output them, right? So actually, the degree to which you can work with the values that are in the frame buffer as they exist is very limited. It's not arbitrary like almost everything else in the programmable pipeline now is. What that means is there is still a concept in OpenGL and pretty much everything else, every API, of the blending stage, which is this stage right here, is still a very fixed function thing. The blending stage still looks basically fixed function pretty much the entire time, even if you're on very programmable hardware. Although, like I said, some hardware that's starting to change, but a lot of it's not. What that means is the equation for how you interact with the frame buffer is actually fairly fixed. It typically looks very, very similar to the kinds of stuff we were doing, where, you know, the output pixel, right, so the color that comes out has to be equal to, let's say, the color of whatever we're doing right now. So let's say like the sprite color, you know, plus whatever, well, I guess we'll say source and destination, because we used those terms before. So, you know, I've got the frame buffer, and that's going to be equal to, that's my destination, that's D. And then I've got the sprite, you know, and that's my source. Whatever I compute for the source color that I'm doing and the destination color, typically I end up with a result, and I guess I could call that D prime. The new result in the frame buffer is basically just some combination of these two values. And really all you get to do is choose these things. Now, fortunately for us, these two things can be chosen to be based on whatever, based on the S and Ds themselves a lot of times. So we don't have to pick constants, thankfully. Which means that if we want to reproduce our blending equation, because hopefully you guys remember this, I've said it so many times, the blending equation, right? Do you remember this? 1 minus t plus t, right? The linear blending equation, which we've talked about so many times, the thing that I said was the one equation I'd take with me on a desert island when somebody asked, right? The linear blending equation, we can create that by an equation that looks like this if we can set a equal to 1 minus t and b equal to t, right? We could do a linear blend. And to do an alpha blend, we kind of know what that looks like, right? We know what an alpha blend looks like. The destination color, right, whatever the destination color value is that we want to write to the frame buffer, we know exactly what that would be. It's whatever the source value is. In this case, if this is the whole pre-multiplied, remember we did pre-multiplied alpha versus non-pre-multiplied alpha? In the non-pre-multiplied alpha case, it would just be whatever the source's alpha value is times the source color plus 1 minus whatever the source's alpha is times the des color. So basically, the alpha value of the source would blend between them. But since we're using pre-multiplied alpha as for all of our sprites, for reasons we talked about back in the pre-multiplied alpha discussion, we don't need this term here. So it's just SC plus 1 minus SA DC. That would be the equation for a pre-multiplied alpha blend, right? So going back to this equation, we know what we would set a and b equal to if we want to do this exactly. Well, a is right here. It's just 1, right? And b is right here. It's 1 minus source alpha. So we know we could set up a blend with an equation that looks like that would be just like our pre-multiplied alpha blend. It just looks like this. So the question is, does OpenGL give us a way to set exactly those things? And as you may have guessed, it actually does. So what happens is, oh, texture 2D is on by default there. That's not what I was expecting. Let's turn that off by default at the moment. Well, you know what? Let's turn it on by default, and what we'll do, since we mostly texture, is we'll just turn it off when we're not texturing. Okay. So yeah, so that is how that would work. That's all good. But point being, so we now need to look at this blending thing. The way that that works is you have to say that you want to use blending, because by default the blending is not on, and you get what we saw before, where like our sprites just kind of render to the screen completely opaque. There's no transparency at all. So if we enable GL blend, everything's great, except we need a way to specify that equation. And the way you specify that equation is GL blend func. It's like funky. And GL blend func allows us to specify what we want the source factor and the destination factor to be. Okay. And so if we say GL blend func, we can now specify essentially the alpha and the A and the B from our equation before. Remember I said I wanted the A, which is the source, the thing multiplied by the source, to be 1. Well, you can see that GL1 is one of the things that we define, that is defined. So we can set that. And then the destination factor, oops, didn't mean to hit that hotkey. The destination factor, what we said we wanted, right, because let's go back to our board here, was 1 minus source alpha, right? So let's see if we've got that. Well, hey, look, GL1 minus source alpha right there. It's almost like the hardware set up to do this, parentheses, it is, because this is one of the main things you might want to do. So if we enable that and then we run, then you can kind of see that now we're successfully reproducing our image again. Yeah. You can kind of see what it looks like when we look at it there. And now we really just have that problem that we're super slow because we're sending the texture down every time, but otherwise we're correctly reproducing it. And I say correctly, there's a couple caveats there too. So we have some work to do, but you know that's a pretty good approximation. Okay. So let's do one more thing so that we can get to the point where it's not so slow as that we want to kill ourselves. And there's a pretty easy way that we can probably do that as well. And that is that in our asset stuff, right, where we have this concept of a loaded bitmap, and I don't remember where that actually was. Yeah, here we go. Excuse me. So you can kind of see our loaded bitmap is a thing that shows up in the asset memory header, right? What we could do is go ahead, and I don't remember exactly where that is defined. I think it's in the platform file. Let's see, grep loaded There it is. What we can do is just cheat here and say, all right, there's just going to be a handle, right? We could just say there's just a handle value, and so that we can totally cheat and know that we're going to be able to submit it whenever we need to, okay? So if we wanted to do that, when we actually do a loaded bitmap and we set the pitch, we got a little thing that says get rid of pitch here. But let's go ahead and see about where we actually load in a line percentage. So inside asset, I'm just going to take a quick look at where a line percentage gets loaded in. It looks like right here. All we would have to do is here set this handle to 0 so that we know that it hasn't been submitted yet. And then what we can do, again, this is a very stopgap kind of a measure. Like I said, I'm not actually trying to advocate anything like this, but all of this code, when I'm teaching you OpenGL, is really just to give you the basics so that you'll understand what we're going to do as we sort of move up through the complexity. So take it with a grain of salt. But if we know that that's the case, then now all we have to do is say, oh, well, if the entry bitmap has a handle already, right? If there's a handle set, then all we have to do, well, either way, we're going to bind it, right? So really what no, that's not true. That's not true at all. What we want to say is if it's got one set, then we can bind it and we're fine. If it doesn't have one set, then we need to set it, right? We need to generate a handle for it. We don't know what this is here yet necessarily. But we need to generate a handle, and then we need to submit the texture. But then after that, we don't ever have to submit it again. So we only need to do it the first time through. We can submit it, and then the graphics card has that handle, and we're good, right? And that's a pretty easy thing to do. Like that's not very difficult, obviously, because inside our code, in fact, we could even do this just with a global variable. It really just doesn't even matter at all, right? We could just do something here with like a global variable to do Casey. Get rid of this. We just need anything at all that will do it. So this is like, U32 next texture handle equals 0. Or maybe just texture bind count, something like that. How many we've bound so far. And so then here we can just say, oh, the texture bind count, we increment it by 1 and use it, and off we go, right? And you notice I pre-incremented it because I want 0 to mean we haven't bound anything yet. Looks like that's not a included thing in the entry, so let's go ahead and fix all of those. And then this should only submit it just that one time, and then in theory it should be able to reuse it after that. So there we go, and now we can sort of see that we're no longer having any trouble with the speed anymore. Everything is much zippier. But there is still one more problem with what we're seeing on the screen right now, as compared to what we were seeing with our software renderer. Our software renderer looked a lot better than this, which I know, see, I knew we had a bug in the sort key thing. Since we happen to hit this, maybe we should debug it. Let's just take a look. Let's just take a quick look. I just want to take a quick look. Because remember we talked about this the other day, and then I was like, I don't want to wait to have to try and have it trigger again, but I'm like, I know it's there. So let's see if we can take a quick look. There we go. Oh, that's just if there are no entries. Hey, look, you can't subtract 1 from the count if there are no entries. That's just a straight up bug in the validation code, ladies and gentlemen. That's always good when you have a bug in your validation code. So this is really an if count. There we go. Fantastic. All right, so anyway, as I was saying, that was nice. That turned out to be easy. If you look at this, you probably can't see it on the stream because the video quality is probably not that good when it's getting compressed and everything. But when I'm looking at it here natively, it's really, really ugly. It's got this sort of shimmering look to it. And if you remember, I discussed all of that back when we implemented bilinear filtering for all of our stuff. And I pointed out the fact that bilinear filtering is what allows everything to look really nice and smooth because you don't get these like these sort of rounding errors that you end up seeing on the screen. So the question is, hey, we got this fancy graphics hardware. Why am I not getting as good of results? I want this to look at least as good as our software render. Come on, this is dedicated hardware people. Why is it uglier than our software render? The reason is this right here. So when we set these up, we didn't talk about them very much. But remember I said these were what were used for filtering the textures, both under minification and magnification. Now, magnification is when I'm taking a texture that's smaller and I'm drawing it on the screen larger than that. Minification is the opposite. I've got a texture that's larger and its screen area is smaller. So it's whether I'm shrinking or growing, and I can pick two different ones depending on which one's happening. Now, I picked nearest, and what nearest was the original way. Like if you go back to our software renderer, that's the original way that we used to do things before we implemented bilinear filtering, where we just grabbed the closest texel in our texture and used that to draw. And then we did bilinear filtering, which grabbed 4 texels from the neighborhood of where it should be and blended based on how far between them it was. Hopefully you remember all that. That's what we need to re-enable. And we can do that trivially by just saying to OpenGL, the filter we want you to use is linear, which in this case means bilinear, filtering of the texture. The reason it's not called bilinear and just linear is because this setting is the same no matter whether it's a 2D, 1D, 2D, or 3D texture. And technically, if the texture was a 1D texture, it would be linear. If it was 2D, it'd be bilinear. And if it was 3D, it'd be like octilinear, right? So they're just saying linear to let you know that's what it is, but it's going to take as many samples as it needs to get the one on either side of the texel for as many dimensions as this thing has, 1, 2, or 3D. Right? And in our case, we're only 2D, so we're always talking about bilinear, but you can understand why they wanted to be a little more generic there. So now we look a lot better. Now we look a lot more like our software renderer. There aren't those ugly jitters in there, and we're back to being okay. So that's basically the hardware renderer in a nutshell. Okay. So this is a pretty reasonable looking thing. But you can see that our ground chunks are kind of messed up, right? And the fact that our ground chunks are kind of messed up is actually somewhat to be expected. Our ground chunks do some very unusual things, obviously, and they reuse their bitmap handles, and there's just a lot of reasons why our ground chunks are going to be problematic. But our ground chunks are a little messed up, but everything else looks about right? Everything else looks fine. Everything else looks good. We can walk around here. Off we go. And so for the ground chunks, I feel like we have sort of a bug there, but I'm not certain I know exactly what it is. We should probably look into that because that looks like some kind of a submission bug. I'm not 100% sure. It's kind of weird. So yeah, I don't really know what's going on with that ground chunk. That's a very good question. So we may have to look at that because I'm not sure. But obviously everything else is pretty reasonable. I don't see anything else that's obviously messed up, right? Yeah, but why those are purple like that, I don't suppose I know. So that's interesting. That's something that probably merits looking into. However, I don't know that we want to look into it necessarily right now because it might not be the best thing to do at the moment. So anyway, point being, this is the hardware renderer running the game now. So our software rasterizer is not operating at all. What you can see, as I sort of suggested, even though this is a graphics card from 2010, so this is a 6 years old, roughly, graphics card at this point. In fact, it's almost exactly 6 years old. I think I got it in March, was when it would have been purchased. It was, yeah, I think so. This is a 6-year-old graphics card, and although it was top of the line 6 years ago, it was 6 years old. You can see that it has no trouble rendering our game, which is why I was sort of trying to impress upon people when they were sort of talking about, is it, do you need to use vertex buffer objects or blah, blah, blah. 2D games are very, very straightforward, and if you don't do anything overtly super stupid, you really don't have to worry that much, as it turns out. Because graphics hardware is sort of so overpowered for what you're likely to do that if you just think it through, you tend to not have too much trouble. So yes, there are things we could do that would tax a graphics card in a 2D game, certainly. Usually it has to do with a lot of overdraw. But at the end of the day, if you're talking about the kind of game that you see normally when, just random Unity game or something, graphics cards should be able to run those just trivially without really optimizing the renderer at all. As you can see, we've done nothing to our renderer whatsoever. It's a little, it took us 10 minutes to write that little loop. I don't even know how long that loop took when we wrote it. That's the entirety of our renderer, and it's fine, right? So yeah. So at the moment, this is all good. There's really nothing problematic about it, but we do have an issue. Multiple issues. And like I said before, they pretty much all revolve around textures. And that's going to be sort of our big problematic thing we're going to have to manage, I think, which is this process right here, where we bind the texture handle and submit it. That is really the thing that we are going to have to work around in the game, because cards are bad at submitting things asynchronously, and our game is set up to stream its assets in incrementally, and that's really the part that's going to be problematic. Okay, so we'll tackle that. We'll probably tackle that starting Thursday, because what I want to talk about now and probably do tomorrow is talk about why I don't love this particular architecture for how to do things. And again, this function is fine. No problems with what we did in this function other than the texture binding part, which is a total hack with the global variable there. Because that texture binding has to be something that gets moved out into our asset system, right? And that's the hard part. So that's the part that's going to be tricky. But if you're putting that aside, the rest of this is totally fine. The only problem I have with it is how it is called, right? And you can already sort of start to see the cracks showing a little bit, even just when you look at it, how we implemented it currently. Couple different reasons. Where's our debug code at the moment, right? Our debug stuff, if you look, isn't there, right? Where's the debug overlay? So the debug overlay is like, oh, right, there was somebody else who calls render group, right? So I got to go down there and now change that call. Where is that tiled? Yeah, there it is. So this is render. I don't remember what we call this group to output. There we go. Is that what it's called? It's in here somewhere. Render to output. Gonna have to work on our naming a little bit. So yeah, I gotta go in there and take care of that guy, obviously, and then maybe we'll have. There we go. So there's our the rest of our stuff sort of working, and presumably I can go up here and interact with these and whatever. But like I said, the cracks are already showing a little bit because really we're sort of doing a bunch of stuff that doesn't even make any sense. Like we're passing a bitmap that's the output target. That doesn't really make any sense, right? So we would need to abstract that away and say there's this notion of a target, but the target is not really, the target is some abstract thing that isn't the same as a bitmap. So that part's a little bit janky, but that's not necessarily so bad. The big thing is you can kind of see how this creates this concept that the game, again, is sort of round-tripping through the platform layer, which means that the platform layer itself has to be set up to service OpenGL rendering in an arbitrary fashion from the game. So there is no way in the platform code to dictate when rendering happens through OpenGL, right? We don't control that anymore. So rather than before, what we had is we call the game, it does whatever it wants, it pretty much never calls us about anything else, right? And then when it returns, it just returns to us the bitmap it wants to have displayed. Well, more specifically, we pass in a buffer for it to fill. We could have done anything we wanted with that buffer, right? We could have saved it to disk to capture it for like video. We could have looked at it and tested it against something for a regression test. We can display it to the screen. We can do all sorts of things about planning when that gets generated. We could save a couple of them, all sorts of stuff. So it was kind of really nice and very clean the way that was separated. The rendering didn't involve, as far as the game knew, any platform stuff. But now it does, and the game has to be aware of this sort of stuff, right? So what I'd like to do is see if we can maybe restore some of that process by considering the render list as the output rather than the bitmap. In other words, just to give you some perspective on what I'm talking about, right now, or I guess we should say, here's what we had previously. And here's what we have now under hardware. So previously what we had is we have the platform stuff does whatever it's going to do, right? Then it calls the game. And what it does is in through here, it passes a bitmap, right? The game renders to the bitmap, and then it comes back to the platform code. Okay, so it's a really nice flow. There's nothing weird happening here. This bitmap gets filled out, and the platform can use it. What we have now is we have the platform code calls into the game, and now the game essentially has to call back out in a round trip through the platform code to do the rendering, right? This is rendering here. And then we come back through the platform code. So it's like a platform game. This happens twice, right? Once for the game render, once for the debug render. So this happens twice, and then we come out through here. And this part is now completely, the timing of this is now completely out of the hands of the platform code and completely in the hands of the game code, which means if there is special knowledge about the platform, about when these commands should be issued, for any number of reasons, the platform code will get much more complicated because it now has to do stuff like defer rendering that comes through this thing, blah, 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 right? So what I would prefer, if possible, is I would prefer treating our render group more like the bitmap. So what I'd like to do is I'd like to see about getting it to the point where we've got a platform, we call into the game, and just like before where we were passing a bitmap, now what we're going to do is pass a render buffer. So like the render group becomes a buffer, it's basically our bitmap. The game is just expected to spew anything that it wanted to render into this big render decision list, basically, a big thing that says, here's all the stuff to render, but it never calls the platform code. And then it comes back through to the platform code again and says, okay, now I'm done. And the platform code can then go look at this, decide what to do to it, either dump it to a bitmap renderer if it wants to, or dump it to OpenGL or Direct3D or anybody else for that matter. And I feel like that's a much cleaner separation. It also allows you to do stuff like capture the output of the game here in a way that you can reproduce offline very trivially and very concisely, which is kind of nice. And it also lets you do stuff like render two different ways if you want to. You could render twice if you were trying to render like, I don't know, you could even imagine doing some stereoscopic stuff automatically if you wanted to by shifting if you record enough information in here, right? So I don't know, it's not a big deal, but I like that flow a little bit better because I feel like it further isolates, it further draws a boundary here, because I really don't like, I find that it makes it harder to port. The more things you have in here, the harder the porting is. And I feel like we've already got more than I would like. I feel like actually this part right here probably should be improved. Honestly, I think that should probably be improved. And so I feel like eventually what I'd like to have is get rid of this, probably have add entry, complete all work, allocate, deallocate, and maybe that would be it, right? So, and of course the ones that are just like for debug stuff, those are okay, but you know, other than that. So I'm going to call it there because what I'd like to do is that's tomorrow's thing will be sort of maybe making that change. So that's all fine, but let's go ahead and go to the Q&A while we are at it. Q&A. Does anyone have any questions for me? You can prefix them with a Q colon. I see no questions. Is there any questions? Questions, questions, questions. Sinocron. Why did you choose OpenGL over DirectX? Well, so there's, I guess there's two sort of maybe answers to that question. One answer is why did I choose OpenGL over DirectX for Handmade Hero? And that's a very easy question to answer. The reason is because there's a lot of people who follow Handmade Hero on other platforms already, even though we haven't ported to Linux and Mac, because one of the things we did on Handmade Hero was make a very clean platform layer separation so that it's very easy to port to other platforms on the whole. People follow along on Linux, they follow along on Mac, they follow along with SDL. And so OpenGL is kind of a very natural choice for us because OpenGL will work on all those platforms. So people who are using multiple platforms on Handmade Hero don't have to go, I can't, like I gotta go learn a totally thing that's not being taught on the stream. Just, you know, I gotta go learn OpenGL even though he taught DirectX so that I can copy it. So Handmade Hero, it's kind of a no-brainer. For an educational series, OpenGL is the obvious choice because it runs everywhere. Whereas DirectX doesn't run anywhere. It's like Windows is the only place you can use it, or maybe if you're an Xbox developer, if those even exist anymore. Assuming that anyone ever buys an Xbox again, which they don't seem to be doing. But that's, I guess in the US they do. So if you're in the US, man, that's fine. If you're in Europe, I don't know. Have they even sold the Xbox in Europe? I'm not sure. Anyway, point being, if you take a look at the broader question of why a developer might choose OpenGL over DirectX, the answer that I just gave is partially true, meaning cross-platform is one valid reason to do it. Like DirectX is a very pigeonhole thing. It only works in really one place, so it may not make a whole lot of sense for you to invest time in creating a renderer for a platform that only exists in one place. But to Windows' credit, it is 97% of the PC game market, so it wouldn't be that big of a deal at the end of the day to maybe use DirectX. Right? So the question then would be, why might you choose OpenGL over DirectX? The primary answer there is obviously that if you want to use the most direct way of rendering on, say, NVIDIA hardware, then OpenGL is like the right choice for that, right? Because the extended OpenGL for specific to NVIDIA, you can do a ton of stuff with like bindless graphics that you just can't do any other way. As far as I know, like you can't do them in DirectX at all. Even DirectX 12 doesn't have support for all of the stuff that you could do, right? So having access to those might be one good reason. But is there a really strong reason to do so? No. You know, I wouldn't say that was true. So, you know, if someone told me I'm making a game and I'm going to target DirectX, I wouldn't be like, what are you, crazy? That's stupid. It's like, no, totally reasonable decision. Again, very reasonable decision because 97% of your market's on the PC. If you want to target DirectX and you don't care about porting very much, go nuts. Also, there are wrappers that can, you can write to DirectX and then wrap it with something that will allow it to run on a Mac through like a sort of an emulation layer, and those aren't that bad because the APIs at the end of the day aren't that different. DirectX 12 is quite a bit different than OpenGL, but like DirectX 11, which is what you'd be writing to nowadays, since 12 doesn't even run on Windows 7, so that's like a non-starter, obviously. Once 12 is more adopted, but assuming you were talking about DirectX 11, they're not that different, OpenGL and DirectX 11. So, you have options there. So, could you do DirectX? Sure. Is it a reasonable decision? Yes. Do I ever bother? No, because I just assume keep things as cross-platform as possible. And I've never had a problem using OpenGL. But, your mileage may vary. So, the Sizek, did you notice that the ground tiles changed when you introduced sorting? Yes, we discussed that on the screen because they were never sorted before, and the splats were never sorted, and they are sorted now. I don't really know if we care about that one way or the other. Like I said, I'm not even sure we're really going to use the ground tiles. We may just pull them because, based on the design of the game at the moment, which is pretty much the final one as far as I'm concerned, I don't anticipate changing it very much. Although you never know. Ground tiles may not really be a thing. But that's sort of a separate issue. Mr. Fourth Dimension, I've asked this before, but I want to hear your case again. What specific things make a data protocol-based interface better than one with function calls? Okay. So I guess I would say that it is a very complicated issue. And I would not say that data protocols are better or worse than function call based protocols. What I would say is they each have very specific advantages and disadvantages that you want to weigh. A data-based protocol, the primary advantage is the ability to non-linearly and repeatedly access what it did, like what was recorded. So if I go and you've already seen this happen in the renderer, if I have a thing that says, here's all the sprites and where I want to draw them, right? And I don't execute that, instead I just keep it in a buffer, I can then do exactly what we did, which is sort those and then render them. So it gives the API abilities it never would have had any other way, right? Because the only way to do sorting in a function call-based interface is to do a recording in the interim. So you're going to end up making that buffer one way or the other, right? So the ability to non-linearly access and to access more than once, right, at different times, the information contained in each call to the API is a very powerful part. Being able to more easily record what happens is a nice bonus, but that's largely because you already did this work of capturing, so you could argue that you could just add that to the other API and get for the same amount of work, right? But that's really the big one. And so I tend to like data-based protocols rather than function call-based protocols because I think they're a happy medium between immediate mode and retained mode. I don't like retained mode because I don't like the synchronization that has to happen. But I don't like pure immediate mode because it doesn't allow enough thinking, right? It doesn't allow that nonlinear access, and stuff like sorting, those sorts of things are very difficult to do. It prevents a lot of optimizations, it prevents a lot of things. So I tend to like the middle, the in-between of those two, which is like an immediate mode style, a thing that looks like immediate mode to the caller, so they get all of the benefits of immediate mode, but with recording underneath, so it ends up being like retained mode in terms of what it can do power-wise. And as an aside, that's why I always say people, I think, tend to misunderstand me greatly when I said the thing about immediate mode graphical user interfaces. What I always meant by that was that it appears immediate mode to the caller. That's the important part. I never meant you don't track state, because tracking state is obviously very important for anything. The immediate mode part is about allowing the caller not to have to care about synchronization explicitly. Just like in our renderer, even though we record everything and do the sorting and then draw, as far as the caller can tell, they don't have to worry about anything. They just call draw, right? And they know that that bitmap will show up at that place. It's as if they had not a care in the world. They don't have to synchronize anything. They don't have to manage lifetimes. They don't have to call free on anything. And that's very important. So I hope that gives you the perspective that you were asking for. I don't know if that answers the question, but hopefully it does at least a little bit. How is vsync controlled? How is vsync controlled? Vsync controls in OpenGL, vsync is controlled by extension call, which I have intentionally not talked about yet, and that is because we haven't talked about how to get extensions. So in a couple days, after we're kind of done with the rest of the stuff that we need to do, when we do extensions, we'll be able to turn vsync on. Kuberkilib, does the GPU do sRGB correction automatically? Yes and no. It depends what you mean by automatically. Right now, it will not be. Meaning right now, we are sRGB incorrect, if that makes sense. When we start working with extensions, in fact, I should probably just write these down so we don't forget the ones that we need to do. We never talked about hardware rendering, we just kind of did it. So here we go. sRGB, frame buffer, and textures. And then we have vsync, background texture downloads, render to texture question mark. I don't know what else, but probably those are the ones that are feature-wise. Obviously, there's stuff like shaders, but shaders is not a feature. It's just something we might want to do eventually. But it's not a feature we actually need because we didn't do any of that in the software render at the moment. So, yeah. Pseudonym73, I wasn't paying close attention, but has the OpenGL texture name thing broken hot reloading? Well, it involves a static variable with the stupid way that we're doing it right now, the way that I said we weren't going to keep. So that should break because there's a static variable. Other than that, no, it would be fine. I think that's the only thing that you would have to be concerned about. Does the GPU do sRGB correction automatically? Yes. What languages do you know? I know a little Japanese. Are there any performance reasons to choose compatible OpenGL API versus Core, or is it just the fact that we get to use programmable shaders in Core? So I'm not sure I totally understand the second part of your question because in OpenGL, both the compatibility version and the core version allow programmable shaders. I'm assuming you're talking about if you do a query, a wiggle create context attrib arb call. I'm assuming that's what you're talking about. Which we haven't covered yet in the stream, so if you don't know what that is, don't worry, ignore this answer. We'll get there. If you do one of those calls, if you pass the compatibility bit versus not passing the compatibility bit has nothing to do with whether you get access to shaders. The only reason that I know of why you would not pass the compatibility bit, I typically don't anymore, but the reason why you might not is to avoid not running on cards which don't support it. because not all drivers have to support, drivers are under no obligation to support compatibility. So yeah, that's what I would say about that. Like NVIDIA drivers just work. You can just ask for a context that supports both shaders and the fixed function pipeline, and it just works. But at least that was my experience last time I tried that. But you know, not all drivers have to do that. And so to remain maximally compatible, I just feel like it's safest, you know, going forwards to just go to core, because there's no real need for the compatibility context. Evine, is there any good reason for desktop GPU to not have programmable blend modes? Because I've seen that most mobile GPUs have that. Yeah, there are a lot of good reasons. Not being a hardware designer, I'm not really in a position to like rigorously defend that position. But what I will tell you is that the place where triangles actually get resolved. Let me go ahead and talk about this here. You know, if we're talking about an entire frame buffer here, so there's two ways of rendering this, right? There's tiled and non-tiled, right? So a tiled renderer is one that looks like the one we wrote, okay? Where you divide the screen up into tiles, and each core is like working on a tile or something, right? And then like some other core is like working on this tile. So here's core A is working on that, and core B is working on that, or whatever, and off we go. And that's the way a lot of mobile GPUs work. So mobile GPUs, I should write this where it actually belongs. Mobile GPUs are usually tiled. And to be honest with you, I don't really know the reason for that, but I believe it's because of the memory architectures. So what happens is, if you don't have like giant special memory controllers with tons of special memory, you know, with tons of wattage and all this other stuff, I believe it's a lot easier to have each of these cores have like one tile's worth of frame buffer memory on the core, where it can just quickly read and write from the frame buffer. Because remember, every operation you do like reads and writes from the frame buffer, right? It's the one piece that just gets read from, read, write, every pixel, every time, right? Read, write. Because even if you're not reading the color value, you're definitely reading the depth value, right? So it's, and so I think on chips where they're more resource constrained, like they are on mobile, less wattage, less memory bandwidth, less memory, specialized memory controllers, whatever else, I don't really know. I feel like it's this big boost to be able to have that small piece. Whereas on regular GPUs on the desktop, they don't typically do that, I don't think. I'm pretty sure they're non-tiled. And they are more arbitrary access based. So they can do a lot of things like unordered access views, right? I don't know if you've ever heard those, UAVs, or compute shaders would be another one, where it's just general purpose code. It can scatter, it can read from everywhere, it can write from anywhere. There's no coherence to it. Implementing these sorts of things, right? There's reasons why doing these sorts of things incurs a bunch of performance problems, right? And by having blending be a thing, so I guess there's two things I should say. So one thing is desktop chips can certainly do those things, and they can do those things specifically because they don't need to be tiled, but they're definitely a much worse thing to do, because anytime you're talking about stuff that's kind of scattery-gathery like that, you have these sort of contentions where different cores of the GPU are contending for the same resources at the same time. Like somebody's trying to read from here, like someone's trying to read from this point on the screen, but someone else is trying to write to that point on the screen, right? And like what happens, you know? So anytime you're in those general purpose kinds of things, you have to start dealing with things a little bit more seriously. Anyway, point being, in order to get good performance, when you're talking about something that doesn't involve breaking the thing up into tiles based on ownership and not really letting things go outside of the tiles. What ends up happening is you have to start having ways of resolving all of the stuff that has to come from and go to the frame buffer. And if you allow arbitrary code execution to happen at that stage, when things come from and go to the frame buffer, which is the blend stage, it was 2 stages actually. It's the alpha test stage and the blend stage. So it's like the pre and post part of the shader. If you end up in a situation where that's programmable, you have no ability to build special purpose hardware in either the memory controllers or like welded into the chip for very fast execution or whatever. The ability to negotiate that very, very sensitive part of that process, which is extremely heavily used, right? So I think, and I could be wrong, but if you were to ask a hardware vendor why they don't want programmable blend, I think it's because allowing that to be a very well-known equation allows them to move that to places that allow them to do very fancy, a lot more general purpose stuff, and allow them to not have to break things up in the way that they have to happen on mobile, for example. I would also say similarly that is why you don't see arbitrary texture unpacking. So, for example, why do we have texture formats at all, right? Why do we have DXTC texture compression? Why don't we just have a shader that's like code that says how to decompress a texture, and then you could implement whatever texture you want? Same reason. That's such a heavy bandwidth part of the pipeline, pulling those textures in, that a lot of stuff, like I think like bilinear filtering and stuff potentially, but also like more importantly the texture unpacking and like stuff like this, really has to be in a very tightly optimized piece of the silicon that's able to do that specifically, and that doesn't have to worry about stuff like arbitrary code execution. So I don't know. You would have to ask a hardware designer for the real complete answer, but my suspicion there is that because they allow this more broad thing and because they want to be able to be fast, they need those 2 critical parts of the pipeline to really have a known behavior. And I think eventually they'll become programmable, but that's why they're kind of long holdouts. Let's see. Do we get gamma correct rendering for free now? Yes, but not till we load extensions. Or rather, not till we use extensions. Base OpenGL did not have the concept of sRGB. So we have to actually turn it on. But yes, we will get it for free. Well, I mean, as far as we know, the graphics cards typically don't have a cost for that. They usually have color lookup tables and stuff to handle it. Cubic, doesn't the OS automatically vsync you, or does that only apply in windowed mode? I don't think the OS automatically vsyncs OpenGL. Normally, OpenGL is allowed to tear unless you ask it not to, so I'm pretty sure we're not vsyncing at the moment. Robbie, so Gamma Curve is also an OpenGL extension? Yes, it is. Long Brilliant, I know you're probably sick of all the Vulkan questions, but here's another one. A lot of places online frame Vulkan as the next version of OpenGL. Their thought being that once Vulkan is released, development adoption of OpenGL will dwindle to the point where OpenGL drivers are no longer developed by graphics manufacturers. Could this happen? And in the event that it does, what is your... And then that's the end. Oh, cute plan. Let's see. And let me see what the other one is. By shooters, I mean GL source and GLGen programming, compiling your shooter source files, etc. I don't know where that question from Elvin was. Oh, he was talking about my thing of shaders, right? Okay. So yeah. So to answer your question, Long Boolean, so my opinion is that there is no way OpenGL will go away. Full stop. Yeah, I don't think it's gonna. At a minimum, you will still be able to get an OpenGL layer that's implemented on top of Vulkan, but there's just no way it goes away. Like, period. I just don't think it's gonna happen. But I can't really say more than that. I mean, maybe like after several revisions, Vulkan could replace it or something. Like maybe 10 years from now. But in the short term, no. No way. Let's see here. Bradshaw and NM, you say that the APIs are very similar, but is there a visual effect that can be accomplished on DirectX and not on OpenGL or vice versa? A visual effect? I'm not sure what you mean by a visual effect. Probably not. But there are definitely things you can do with OpenGL that you can't do on DirectX. That's definitely true. In terms of like features of the hardware that you can access. And SZ, is there a good reason why Windows OpenGL headers only offer the old legacy stuff while other platforms add new stuff? Yes, it's because they want to force you to use DirectX. It's the same answer it's always been. They wanted to kill OpenGL entirely, but they failed. So if they had their way, there'd be no way to load OpenGL at all. But yeah, that's why they haven't been supporting it. And it's lame, honestly. But that's just the way it is. At some point, can you go over the pros and cons of the different graphics APIs? To be honest, I really don't think there's that much more to it than what I already said. OpenGL has better access to hardware features because it allows driver writers to expose extensions more readily. DirectX integrates with some Windows features better. Beyond that, there's really not much difference. DirectX 12 is more equivalent to Vulkan than OpenGL, so the comparison there is probably between Vulkan and DirectX 12, whereas DirectX 11 is comparable to OpenGL. But really, yeah, I mean, is there a strong reason to use DirectX or OpenGL? If you're only on Windows, I would say it really just does not matter very much. At least I can't think of a lot of reasons why you would care that much. I guess one thing about OpenGL is it's more compatible even on Windows. So for example, OpenGL, you can target any version of Windows, whereas DirectX, you can only target the Windows version it's shipped with. So for example, DirectX 12 only runs on Windows 10 or whatever it is, I guess. Is it 10 or 8? Whatever it is, you can only run DirectX 12 on that. DirectX 11 only runs on like Windows 7, right, and up. DirectX, 9 only ran on XP and up or something. I don't know what the versions were, but Windows, they never backport, or they didn't used to. So that was another reason why you might want OpenGL, because you can keep one code base across all your versions of Windows, and you don't have to have DX9 and DX11, for example. Like the Witness had to ship with DX9 and 11 support, I think, for that reason, which is really annoying. So yeah, so I don't really know. To be honest, I don't know why you would use DirectX, because I can't think of a positive aspect of it. The only thing I can think of is maybe it runs better on some machines. If like AMD's DirectX drivers are better than their OpenGL drivers or something, maybe would be one reason too. Other than that, I don't really know of a. I can't think offhand of a positive reason to use Direct3D rather than OpenGL. But at the same time, I also can't think of a huge number of like overwhelmingly important reasons why you have to use OpenGL. So that's why I say if someone wants to use DirectX, I can't think of like some super important reason why I'm like, oh my god, no, don't use DirectX. It's like, no, you know. All right, I'm gonna call it a day here. I'm gonna call it a day, folks. Let's wrap this up. Let's wrap it like vanilla ice. All right, I'm gonna close this down. Let's see. Let's see. Close. Close. All right, everyone. Thank you very much for joining me for Handmade Hero. It's been a pleasure coding with you as always. I hope you have enjoyed this foray into hardware accelerated rendering. As you can see, there's not really that much to it. It's not some big mystery. It's just a simple matter of piling up a bunch of commands that you want your graphics card to do, and it does them. We will be exploring a few more issues with this. Tomorrow, I think I would like to do that pipeline abstraction that I talked about, just to kind of rearrange the way that works. And then we'll have to start on the what I think it will be by far the hardest thing we'll have to do for our hardware rendering support, which is just how we want to get textures downloaded in an efficient and reasonable manner. So that part will be a little tricky, but I think that's the only part. If you want to watch that, be sure to come back tomorrow. I think we're 8 p.m. Pacific Standard Time. Check the tweet bot for sure, but I believe it's 8 p.m. tomorrow for the stream. Love to see you there. Until then, if you want to follow along with the series at home, you can obviously go to handmadehero.org and pre-order the game. It comes with the source code if you want to play around with it and follow along at home. It's a great way to learn from it. Also, you can go to our forum site where you can ask questions and talk with other people about the series. We also have a Patreon page where you can support the video series by subscribing, and we have the aforementioned tweetbot, which tells you when we are live. It's a good thing to check so you know when the series is going to air if you want to catch it live. That's about it. Until tomorrow, have fun programming, guys, and I will see you guys on the internet.